Thank you. So I'm going to present a work called Fairness Classifier via Transferable Representations. So it's a joint work with Thibault Le Thénault, who's a PhD student at Université Jean Monnet, Michael Perrault, who's a researcher at INRI à Lille, and Antoine Mourou and Christophe Gravier, who are also both assistant professor and professor respectively at Saint-Etienne. And so what's nice is that I'm going to go quite fast on the first few slides because it's very similar to the setting presented by the first speaker this morning. So again, I'm going to talk about fairness classifier, but this time I'm going to focus on a very specific application, which is text classification, and I will show how we want to use these specificities in our setting. And so it's nice she used this example actually to motivate why we are interested in fairness. So let's assume that we are a HR service, and we want to set up some machine learning model to do resume screening. Okay, so we want to take someone's resume, extract the text from it, and then predict what is the job of this person or what job she should be occupying. Okay, and so for several resumes, we're going to have the resume and then the job assigned to it. For instance, this person is going to be set in the class of designers, and then we will have another resume, and she will be like a surgeon and not a nurse just because she's a woman, and that's the whole point. And I'm going to end up with a bunch of labeled resume. Okay, so I'm going to have nurses, yoga teachers, architects, designers, surgeons, etc. And now I'm going to assume that I have a client coming and he needs an architect. So I'm going to use the label that I've learned on this resume, and I'm going to extract the resumes that match this job. Okay, and if I analyze what's going on here, and let's say I have 100 of resumes that are actually architects, and I can end up in this kind of situation. Okay, so out of the 100 applicants or candidates, I'm going to have 85 men and 15 women selected by the HR. Okay, and so you have two routes which are possible for this kind of issue. Either the firm actually only gathered 15 resumes of women who are architects, or the classifier that assigned the jobs to the different resumes is biased. Okay, and we are going to go with the second possible route and assume that the problem comes from the classification and not from the population. What's interesting, so Solène mentioned that one of the starting points for studying fairness is the study that was done by ProPublica, so machine bias, the Compass scandal. And it was actually published in 2016. Whoa.
Beat.
And this is also...
Because it...
Okay. And this is also in 2016 that people started to notice that word embeddings could also contain a lot of bias. And these were done quite in parallel, actually. It was not directly connected because the task is very different. So word embeddings date back from, I don't know, 2013, I think it was word2vec. And it was quite fascinating for the community because suddenly you could do like simple operations on words. Okay, so you just take their representations and you could sum or subtract these words. So basically, if I take king, okay, and I do king minus male plus woman, then I get queen. Okay, these kind of operations were very interesting and fascinating. And the problem is that you can do this for like this kind of examples, but then they also realized that because of that, embeddings can also can also encode a lot of bias, and notably what they realize, if, for instance, if you take surgeon minus man plus woman, then you were getting nurse. Okay, so this is the type of bias that we realized were there. Okay, and so the first paper that was addressing this problem was also from 2016, and it's called Man is to Computer Programmer as Woman is to Homemaker. And as we know, now we're not doing word2vec anymore, we're using like large language models, but the problem is still there. You're still learning embeddings. They're just more efficient to solve the task because they have this capacity to take context much more widely into account, but the problem is still there. So you have different types of fairness that you can consider. That will go really fast here because this is the same as Solène mentioned. So I'm going to be in the setting of group fairness. So saying that different groups of people should not be treated too differently. And so with my previous example, for instance, I'm going to want the selection rate of females not to be too much lower than for males, for instance, for a particular job. And so the setting that I have is the following. So I'm going to consider triplets, and I have a corpus of n of them. So these triplets are basically documents. So xi here is going to be a short document. Y is a label, so for instance, predicting the job of a person. And I'm going to have a sensitive attributes for each of these documents. For instance, the resume is a resume of a woman, okay? And this is like examples from a very well-known data set in the community, which is called bias and BIOS. So for instance, here I have X, which is she's able to assess, diagnose, etc., okay? She's a nurse, so that's the Y that I want to be able to predict, and she's a woman, okay? And the second data set that I'm going to use is the one that is trying to do sentiment analysis, so it's still a classification problem. And this one is called Moji, I think. And so you have tweets, and you want to predict the sentiment of the tweet, and then you have the origin of the person who did the tweet. Okay, so those are the two kind of data that I'm going to be dealing with. Now to measure fairness, so again, I'm going to use the same metrics that were presented this morning, just written a bit differently, so I'll still spend some time. So here I'm referring to it as demographic parity, but it's the same as statistical parity that was presented. And so basically, if I take, so this is what I had. So if you look at this figure, okay, you can see, for instance, here that the probability of being predicted to be an architect is going to be 30% if you're a man, and then much lower if you're a woman. So if you are going to target demographic parity, basically, you want these to be the same, okay? And so when dp for a given value of the sensitive attribute ny is greater to 0, it just means that the group with protected attributes receive the prediction y more frequently than the overall population, and then less frequently when it's below 0, okay? And the second metric, so already mentioned this morning, pretty much the same, but this time you're going to condition on the true distribution, because you don't want to just select people just based on their sensitive attribute, okay? You also want them to be qualified for the job. Now, in the literature, a lot of people decided to try and address this problem through mutual information minimization, okay? So it's just one way to measure the dependence between two features, and some people decided to try and reach demographic parity by minimizing some mutual information between the label and the sensitive attributes, y and a. And then for equal opportunity, the same type of approaches have been proposed, but this time conditioned on the true y. Should be y hat in my ME. Okay, so just a recall on mutual information, I'm going to need it to introduce the one that we are going to use, which is not mutual information. So for mutual information, for two random variables x and y here, with joint distribution p of xy is in the marginal, okay? So the ME is just a Kullback label between the joint distribution and the product of their marginals. And it presents a lot of like limits, and empirically speaking, one of them is that the lower bounds to the mutual information are only tight for sample size exponential in the mutual information. So let's, so it's a result from McAllister. So if you look here on the left, so it's working. Okay, so you can see here the solid line, okay, the black one is the mutual information, okay, the value that I want to estimate. And then I've used like several approaches to estimate, okay, to approximate this mutual information. And then I'm going to, as training steps are passing, okay, I'm just going to add batches of data, okay? And you can see that as I add data, then my estimates are getting closer to the true value, okay? But they're getting closer very slowly. So it means that to have like a good approximation of mutual information, I'm going to need a lot of data, okay? And the second problem is that it's quite sensitive to small perturbations in the data samples and not aware of the metric of the underlying distribution. So if I take, so this is the same example as this morning. So I have two Gaussians here. The only difference is that one has a mean of 0 and the other one has a mean of 2. Is that if I compute the Kullback, I get something like 166, which means pretty much nothing, okay? These are just two Gaussian shifted. But then if I take the Wasserstein distance that was presented to you, then I get exactly 2, okay? shift in the middle. So this is the mutual information, and I've presented that Wasserstein does a better job at estimating the actual distance between distributions. So without any surprise, we're going to use something that is based on Wasserstein to replace this mutual information. And the measure that we want to use is called the Wasserstein dependency measures, and it was proposed so in a very different context in 2019. And it's just expressed like this. So for two random variables, x and y, it should be capital X, capital Y, sorry for that. Then the Wasserstein dependency measure is the Wasserstein distance between the joint distribution and the product of the marginals. Okay, so it's exactly the same thing that I'm putting then for the Kullback when I'm computing the ME, but this time I'm not doing with the Kullback-Leibler divergence, but just with the Wasserstein distance. Okay? So this is my... Okay. Okay, so this is the measure that I'm going to try and use in a classifier. Okay, so just to recall, this is my setting for fair text classification. And before explaining how I'm going to integrate this measure into my classification pipeline, I'm just going to recall what a classification pipeline for text resembles nowadays. So I have some text here, okay, so this is the same text that the one I presented, so this is X. I'm going to just encode X, okay, using this encoder here. So I'm just going to project the text in some embedding space of low dimension, okay, and the way to do this today is to use any puppet, okay, so Bertha, all of these pre-trained language models are doing actually the job pretty well. You could also go for more modern approaches, but this one are working really well. And this is the encoder, and it's going to produce Z, okay, which is a representation that has been learned for this text. And like I said, it's in a dimension that we can control, and here it's going to be this D. Once I have this Z, I'm going to pass it through some classifiers. So it's usually just a multi-layer perceptron with few layers, and it's called also the classification head, okay? Apply the softmax at the output, and I'm going to get some probability for each of the job. Here, for instance, here, if I pass this document, then I'm going to get a probability of 90% that this person is a nurse, okay? So that's the setting, that's notation I'm going to need. And what I will say is that somehow you can say that the composition of the classifier before the argmax operator and the encoder, okay, is some kind of scoring functions that I'm going to call pi. All the rest up to there is clear. Yes. Okay. So now what do I want? Okay, I said I want fair text classification, but I don't want to stop there, okay, because you have a lot of approaches that are actually doing fairness and classification at the same time. So the first thing I want is obviously that the prediction of my classifier must be independent of some sensitive attribute. So this is a classical wish, let's say, for this kind of problem, but then I'm going to add two of them. And the first one is that I want to be able to handle any type of sensitive attributes, okay, whether it's age or gender. I don't want for that to make any difference in the way that I'm going to be working. And this is already something that differs a bit from the literature, because usually we restrict ourselves to, let's say, binary attributes like woman versus man. And the last thing, and this also resembles some of the things that have been presented this morning, I want to be able to work even when I'm not aware of the sensitive attribute, okay? So I want the approach to work even when I have either incomplete access to sensitive attributes or non-access to these sensitive attributes. So the first thing, like I said, so I'm going to present the theoretical results, but I'm not going to go in details on how we get it. I just want to give you the insight of what they mean for us, okay? So the first thing that we had to check is the Wasserstein dependency measure a good way to actually reach some fairness optimization? So here we have this first results, okay? So we have IW, which is the Wasserstein dependency measure. We're going to consider A, Y, and Y hat are random variables. So A is the sensitive attribute, Y is the label that I want to predict, and Y hat is the estimate. And what we were able to show is that the Wasserstein dependency measure between the prediction Y and the sensitive attribute is actually exactly equal to some linear combination that involves the demographic parity that I presented before, okay? And we have the same result with equal opportunity. So the only thing we have to remember for that is that if I minimize this term, then I'm actually really minimizing demographic parity or equal opportunity, okay, on the other hand. And the term that you have here, it's just the proportion of, you can see it as just the proportion of people who are going to have that actual sensitive attribute, okay, and it makes sense that it's there in this result. So, okay, now we know that if we minimize this dependency measure between well-chosen random variables, so for demographic parity, the variables are going to be y hat and a, and then for equal opportunity, it's going to be y hat condition on y, okay, and a condition on y. So now how do I integrate this? And so I show you the pipeline, and the good thing with fair text classification is that it's fully differentiable, and we want to keep that, okay? And we also want, like I said, to work in a case where A is maybe not accessible. But, so this is the, let's say, intermediate objective. So I have my pipeline, and then the loss that I'm going to try and optimize at the end is just this loss, okay? So this is just the traditional cross entropy, okay? So I'm just going to check if my classifier is actually managing to predict the true y. And then I'm going to regularize with the Wasserstein dependency measure, and I have this hyperparameter. It's very common, okay? This is beta, and it's going to control the level of independence that I'm going to put. And there is like a well-known type of results in fairness that if you have, when you increase fairness, you usually decrease accuracy, and this is why we have beta. We don't want to destroy everything, okay? So, okay, we have the first, let's say, the first wish done. And then we wanted also to manage like not having access to A, neither at training or inference time or even at all, okay? And so what we did is we just decided to approximate A, the same way we are actually estimating Y, we can estimate A, and this is why it's called like from A to A what, and we're going to use something that we call a surrogate model, and in the following I will just call it a demonic model because his job is to predict the job, okay? So the pipeline is the same as when we are trying to predict Y, but this time, we are trying to predict A, so the sensitive attribute directly. And so what I'm going to do is that in my optimization function here, I'm just going to replace A with hey what, okay, hat way, at hey. And what's nice by using this surrogate model is that I don't have to train it at the same time than my classifier, okay? I can actually pre-train it, and I can even pre-train it on some other data set, okay? So what do I lose if I do that? Okay, because I'm doing an approximation of A here, and okay, again, this result is actually very intuitive. I'm not losing so much, and it's actually depending on how good I am to predict A, okay? If I'm really good at predicting A, then it's going to be equivalent to minimizing the same thing as before, okay? So it's the true A. And here, basically, as my demonic model gets worse, then this bound gets looser, okay? So I need to have a demonic model that's doing a good job. That's what we want to recall. And okay, again, direct application of Vapnik dimension theory. I can just estimate this like theoretical error epsilon with epsilon hat, but okay, there is nothing very fancy here. I've just replaced the true error, okay, of the surrogate model by its estimate, okay? What we have to just remember is that it shows that if we minimize with the approximation of A, we are still minimizing what we had in mind at the beginning, and it's only tight when the demonic model is accurately predicting the sensitive attributes. Okay, now a setting that we were very interested in is what do we do when we don't have access to the sensitive attribute at all, okay? So I have, for instance, this bias in BIOS, and then I don't know, a lot of information has been removed to be RGPD compliant or whatever, and now I still want to use this pipeline. Then in this case, like something we would like to be able to do is to rely on some other data sets that have access to that attribute and that can be synthetic. And with text, it's actually pretty easy if you think about it. The way we talk about, I don't know, woman in text is pretty similar, whether it's in a resume or like, I don't know, in a tweet, okay? You're going to see the same type of words coming like she, he, her, etc., okay? So you can think that, okay, it should not be so hard to transfer that kind of knowledge. And what we want to do is even to go further and work with synthetic data sets. And you have two of them in the community that are used. So the first one is the Equity Evaluation Corpus, so EEC. And it's a data set that is like what we call template-based generation with some list of noun and name. So they gave templates, like the conversation with person as was, and then some emotional situation word. And then they had lists of person, lists of emotion situation words, and a list of templates, and then just tried every combination that you can think about. So for instance here, the conversation with my mom was displeasing, the label is anger, and the sensitive attribute is woman, and you have, like, you can use this template again and again. So my husband feels scared, and it's fear, and it's talking about a man, okay, so A, here is the man. And you also had it with like some common names that you can find in some particular community depending on origin. So for instance, Latisha feels glad, she's happy, and Latisha is a name that's typically African American. So there is this first data set. And then the second one that we used is called marked person. So it was generated, not surprisingly, by GPT-4. And what they did is that they tried to generate some personas using the same prompt. And the prompt was the following: describe A or N, and then they were like putting some ethnicity, gender, and then from the first person perspective. So for instance, if the ethnicity was Asian and then the gender was woman, then the text was generated something like this. So I'm not going to read it from the start to the beginning, but what it says is that what they remark is that some terms were actually coming back more often for some ethnicity or for women, okay, in terms of character and so on. And so they generated like this bunch of text for which we actually have access to information on the sensitive attributes, okay? And this is another example for like white and men to fill in for like ethnicity, race, and gender. I shouldn't move at all. Okay. And if you, okay, let's go back to the results before. So if you remember, I had the following thing here, okay, but then here I was just assuming that the A what, that the hat height, okay, the estimated of A was actually learned on the same type of data, okay, on the same sample than the one I was going to be training my classifier after all. So obviously, what we expect is that this term is going to remain, obviously, but this term is going to be drastically changed. And notably, what will appear, okay, if we want to have this transfer capacity, is something very related to domain adaptation. So I don't know if you're familiar with like covariate shift in domain adaptation. Yes. Okay, so very quickly, imagine you want to classify images. You have very good quality image, and then you have quality. You have other images with very low quality. Okay, the fact that you have a very low quality is not changing the relationship between the image itself and the label. What's changing is actually the distribution of the images. Okay, so this is covariate shift, and this is also what we want here to assume. Okay, this is the setting we are in, and so what we get is basically the same. So if you assume that now you have some source data and some target data. Okay, so here the source data is the one that I don't have access, that I have access to, and the target I don't have access to, okay? And then I'm assuming that I'm this covariate shift setting, then I'm going to get this type of bound, okay? So the first term here is the same as before, this constant is the same. And like I said, okay, what's going to be changed is that now I'm not only having this like true error of the demonic model, but I have something that depends both on the error of the true model, so it's somewhere hidden in the epsilon and the lambda here. But I have something like here, which is this delta divergence between the source and the target domain, okay? And so the only thing that this tells us, this is like direct application of Ben David and al, who did a lot of stuff on domain adaptation. So what this is telling me is that if my source and target domains are not too far away, okay, then this bound is very similar than the one that I presented before. So if I take, for instance, resumes that have been written for like HR, and then resumes that are posted on LinkedIn, okay, then the source and the target domains are very nearby. So I'm going to expect this divergence to be really small, okay? But on the other hand, if I take, I don't know, technical articles, like scientific machine learning articles, okay, and I'm trying to learn gender prediction on that, it's going to be really hard to transfer on anything else, okay? However, what's nice is that now we can operate independently on the axis of A, okay? And then what's nice is that the model can even operate without access to A. The only thing we have is that we need to control somehow this term here, okay, so that the bound doesn't get too loose. Okay, and then we did one last thing. I mean, we are approximating from the beginning, so let's keep on doing it. And like I said, I want something that's fully differentiable. And the problem is that in the pipeline I've shown you, in the end, okay, to predict y, I'm going to use the argmax. And it's not differentiable, and then it's going to be a problem for me when I want to do the regularization properly. So what I'm going to do is that instead of taking these two estimates, I'm going to replace them by the representation that I've learned in my model, okay? I'll show you at the end like how we implement this. But very easily, what we just did is that we are replacing the estimated label y, okay, with its learned representation. So it's just the last layer, basically, of the classifier, okay, that we're going to be taken. And then we do the same with A. And it allows two things. First, okay, we are getting rid of the argmax, especially for y. For A, it's not really a big deal because it's pre-trained, okay, so this is not a problem. But at the same time, what's nice is now A can be of any nature, and it's always going to be represented by some vector in dimension, something controlled, and so to compare with y, it's also like kind of more natural. So this is the final loss that we have, okay, for the pipeline. So this is still the cross entropy, and now we are just trying at the same time to regularize with the Wasserstein dependency measure between the representations learned for the label y and for A. Okay, what do we lose when we do this approximation? I've simplified, okay, in the paper, like it's even more ugly. But just to give you an intuition, okay, so we tried to see like what we were losing when we were trying to approximate y hat and a hat, never going to make it. Okay, and so here I have the term that I'm actually going to be working with, okay? And so now I need to like look at what's around it. And what I have is some epsilon, which is basically the confidence margins of my predictions, okay? So if basically before applying my softmax, if after applying my softmax, okay, I have something with a very predominant class, okay, then this quantity is actually going to be really low, okay. And so what you can see here is just that the tightness of the bound is going to depend mainly on the error which is introduced by the softmax, okay. And so the epsilon here so measures how dominant the predicted class is relatively to the others, and then the epsilon here, like there are a lot of stuff hidden in it. But what's important is that it's going to contain the proportion of example for which this minimum confidence is actually not obtained. And what we realize is that actually, so the temperature that we use in the softmax is actually going to help us control the trade-off between this epsilon and this xi. Sorry, it's xi. I don't know what I've said from the beginning. Okay, so just this is something we can slightly control, the terms which are surrounding the one that we're actually working with. And the way to control it is not so easy. So for this bound, it's not like for the others, okay? We have few tools to check that it's actually going to be really tight in practice. I prefer to be honest. Okay. I've shown like one measure, then I'm going to say, okay, we're not going to use that measure, we're going to use one approximation and another approximation and another approximation of that measure. But now I'm going to show how we implement it, and then I'm going to try and convince you that these approximations were actually useful and not and work pretty well in practice. Okay. So first we need to learn the representations, because this is what we're going to put as an input for our Wasserstein dependency measure. So it's very easy. We're going just to take a bunch of documents. For each of these documents, we're going to pass them into this nice like pre-trained language model. So we took BERT in our case, okay? And then use this representation into some input for two MLPs, which are trained to predict both the sensitive attributes, so this is the demonic part, and the label that we want to predict, for instance, the job of the person, okay? And we will take, like I said, we will just take that layer, okay, the one just before the prediction, and this layer is going to be our ZY and ZA. Okay, now we need to compute the Wasserstein dependency measure, and the way to do it, it's inspired by a paper from Wasserstein again, but I'm going to just, I don't know like how familiar are people with this type of results, but we're going to rely on the Kantarovich-Rubinstein validity theorem that was presented in Villani, so by Villani in 2009. And it's just a way to express the Wasserstein 1 distance as a supremum, okay, over all one Lipschitz functions, okay? And more precisely, it's just the maximum difference in expectation, okay, between this one Lipschitz function taken either on P or Q here, if I want to compute, for instance, the Wasserstein between random variables P and Q. Okay, so this is just another way to express the Wasserstein 1 distance. And what's nice is then we can actually, I'm going to show you how we can actually then optimize on this. And so this is what was proposed, what we need now, okay? Basically, if you look at this, we need to find f, okay, that is going to be really helpful for us. And so f is just a function, and our favorite function nowadays are neural networks. So we are going to say that now, if we apply this, okay, to our setting, we are going to end up, so here we have exactly the same, but instead of taking P and Q, we are going to take the joint distributions of our representations and then the product of their marginal, okay? And we are going to parameterize f by just a neural network, which is C here, that has weights omega, okay? And we have many ways to enforce the Lipschitz constraints, like clipping the gradient or the weights, or, okay. So for this, it's not really a problem. But basically what we will do is that we will use this, and what it means is that in the end, the estimation of the Wasserstein dependency measure will be done by a neural network, okay? And it's what we call a critic, and this is what was introduced by Arowski and al. In 2017. Okay, now the last thing we need, okay, so we have the representation, we have a way to compute the Wasserstein dependency measure, and now we need to pre-train the demonic model. And what we want, like I said before, is like we want to have some control over this, okay? And in domain adaptation, what people usually do is that they add a regularization term to the loss function. So for us, it's going to be to the loss of the demonic model, so the one that is trying to predict A. And these regularizations should learn representations from the source and target domains that are both closed, and informative for classification. And so for people who know about domain adaptation, do you have a clue about what they're using to enforce this closeness? Of course, again, the Wasserstein distance. I mean, okay, so this is also something that was already done in a DA. What you can just say is that you're going to regularize the model that is predicting A, okay, with some Wasserstein distance on the representations that are learned on the source domain and the representations that are learned on the target domain, okay? And then we compute it exactly the same way as before, okay? We could have done it more efficiently, but here we just use another critic. Let's put it all together, okay? So this is the overall architecture. So here I have the document that I'm interested in, okay? I have here the first, like this is the text classifier that I want to actually train and make not biased as much as possible, okay? It's predicting Y. And then on the other hand, I can assume that I have some other documents, okay, in case I don't have access to the sensitive attribute, and I'm going to train here the demonic model, and if needed, I'm going to do domain adaptation at the same time, okay? And for these representations, I need to build what is a joint and what is the product of the marginal under independence, okay, because it's not quite natural. So for the joint, I'm just going to concatenate the Z, okay, associated to each of the Y with the one associated to the A, and then to like have an idea of what it will look like under independence, I'm just going to randomly shuffle the one on the right, okay? And I'm going to pass that into my critic. No question? Okay, so just the results. So first, how does it work? Not so bad, obviously, otherwise there will be no papers. So this is two datasets, the one I've shown before, so the Moji dataset and the bias in BIOS, a bunch of baseline. And then you have here our approach. So this is the two bottom rows. And if you recall at the very beginning, I showed results where I was either working with a dependency measure that was conditioned on Y or not, okay? So either to control EO or DP. And we tried both. And what we observed is that actually when you measure fairness, so here fairness is measured in terms of equal opportunity, even in that case you get actually quite like slightly better results. It's not so significant, but slightly better results when just considering like without the condition on Y. And it's also easier to compute. So we kept this one for the rest. And here, so DTO, it's called distance to optimum. So you just take you can build some utopia points. So you take the best fairness and the best accuracy across all the baselines. Okay, and this gives you the coordinate of like some utopia point that you would like to reach. And then you compute the Euclidean distance of your model with respect to that point. Okay, so this is kind of a measure that gives you an idea of what type of trade-off you're reaching. And then the leakage, I'm not going to mention here, but it's just looking at like, can you actually predict the sensitive attribute from the representation that you've learned for your classifier, okay? So here it's just to say it works well, and we decided to keep this one and drop the condition on Y for the rest. So this is the impact of beta, okay, and okay, let's go quickly on it, but you have either demographic parity here and the Wasserstein dependency measure, okay, and okay, so the solid lines are the Wasserstein dependency measure, and the dotted line are the demographic parity, and you cannot see any of the DP because they are all up there, okay, all like matched together. But it was just to show that depending on the beta value that you get, then you actually manage to reach a better demographic parity. It's quite expected, but we still wanted to check it, and we did it for the two data sets. Now we wanted to see like what is the impact of switching from the approximation of A to the representation, okay? Because for A, we don't really have this constraint on differentiability for the argmax because it's pre-trained. And so this is the type of results that we get. And actually, when you use the representation Z instead of the R labels, you're sometimes getting even better results in terms of fairness and both DTO, okay? Or some things which are like quite similar. So for here, for accuracy, it's actually quite close, but you get a very huge like increase in fairness, and it's the same for Moji. So actually using the representation, yet it's an approximation, but in practice, it seems to actually help the model to be both more accurate and more fair. Like this is not something that was appearing in the theoretical results, but I mean, it was nice to see in practice. So they do not deteriorate the results at all. Of course, they do not deteriorate the results because the demonic model is good at predicting A initially, okay? And for the cross-domain training, so here I'm not doing any type of regularization for domain adaptation, and we tried so three things. So it's all the results are for one data set, which is bias in BIOS. So the first line, I'm only taking 1% of this data set to pre-train my demonic model, okay? And this is the type of results that I get. And in these two cases, I'm using the two other synthetic data sets that I've presented before, and I'm using these ones to pre-train the demonic, but then those are the results obtained on bias in BIOS. And the same, okay, you can see that actually here, without doing anything, okay, so just by assuming that the delta divergence is not going to be really large, it's actually working really well, okay? The loss is really small. So for instance, for MP, it's even the same pretty much as when you actually use BIOS. And then otherwise, I mean, the decrease is really, really small, okay? So when the source and the target data sets are quite similar, we actually achieve very comparable results when pre-training on some other data sets. And we wanted to check what's going on if we kind of increase the divergence between the source and the target domain. And what we did is that we built it a bit by hand. So we took MP and we removed every gender word from it. So we removed, for instance, him, he, his, she, woman, man, whatever, husband, woman. So all the wife, I mean, all the words that are like quite gendered, we remove them from the MP to just increase this divergence, okay, between the source and the target domain. And in this case, okay, we checked like what was the interest of adding this regularization term for domain adaptation, and it's actually really helping, okay? So this was just to justify why we are like making the architecture even more heavy by adding this second critique to regularize the demonic model training. Okay, so domain adaptation in this case is really necessary, but only when the source and target's domains differ too much. And if you think about it, like we actually had to build it, okay, the case, but it's something that can happen, for instance, if some data have been kind of filtered out, again, to be compliant with some law, whatever, they can have actually removed a lot of information that could have helped our model to predict the sensitive attributes. So it's good to have this in mind still when working in this type of data. Okay, so if I sum up, okay, so the initial wish list was first to have a classifier that was almost, let's say, independent of some, for which the prediction were almost independent of some sensitive attributes. And we achieved this by minimizing some Wasserstein dependency measures between representations which are learned by deep neural networks. We wanted to be able to handle like any type of sensitive attributes, and actually by considering Z instead of A, we can do that. And we can work in very incomplete access cases, even for instance when we do not have access at all to the data, using the demonic model.
Well, I have a question. When you go to the independence of the probability distribution of the representation Z, you say that if you shuffle, it's going to be like it's independent. I don't quite understand why.
So it's a strong assumption. I agree. Like basically what we say is that initially they are dependent. That's the hypothesis that we have. And so if they are dependent, if you just put, say, serious. So if they are actually dependent, okay, then the joint distribution I just take, so I take ZY here and ZA, okay, for each of the observation, and I just put them side by side, okay, and this is building my joint distribution. Now, I don't know what these distributions are when they are independent, okay, so I kind of need to build it. Like if I want, I'm just assuming that the product of the marginal is different from the joints. And so what I'm doing here is that I'm going to keep the same column the same, okay? And then for the second one, I'm just going to randomly shuffle it. So this time it's not exactly it's not the same representation, because now I'm associating each of the Y with a ZA, which is not the one that was learned for that particular document. So if I take a document, I'm predicting some labels for it. I have this hidden representation ZY. Then for the same document, I've learned like some ZA, but I'm not going to use that ZA. I'm just going to use randomly another one from the data set. And in this case, I'm assuming that if I'm just taking something like at random from the rest of the representations that are learned, then I'm going to have, as like in this setting, then the product of the marginal is going to be different from the joint and represent some kind of independence. They should be independent because they were not learned on the same document, basically.
Okay, right, thank you.
Just to reiterate on the same question, it's like when you just randomly permute, you preserve marginals, and that's how you just destroy dependent, right? Like
Yes.
And are there any other questions?
Yes. So at some point when you present your results, you say that what you want to do is minimize, enforce equality of opportunity somehow, and actually enforcing demographic parity helps. So it's kind of counterintuitive when you think about the impossibility results. Do you have any explanation for that? Or?
For me, but I may be mistaken, but the impossibility results are also like due to calibration in some sense. And I think if we do not consider like calibration, like it's not always impossible. honestly, the reason I think it's like this, it's because it's actually quite hard to compute this, okay? And to do it, we could only use partially the observations that we had. So we are working with less data somehow than when we were optimizing the first one. So probably it's just because we have less data that can be considered, because we have to do this condition on the true y, but we do not have access to the true y because we're at test time. So I forgot, like I cannot explain exactly how, because it's Thibaut who managed like all of this. He managed to find a way that makes sense to compute it, but then he said, okay, I have to basically discard a lot of observations. So probably that can be the reason. Like if we had a more efficient way to estimate what it would look like, condition on y, then the results should be better.
I had a question about your first result when you compare the demographic parity to the transport measure of y and a. So this equality, is it based a lot on the fact that it's discrete? So because I guess if we have a discrete, so the distances between couples can be only 0, 1, or 2.
Yeah.
So does it play? So that's is it the reason why it's an equality? So I was wondering if it generalized to a regression.
We cannot generalize when y is not continuous. We can only generalize when a is of any type. But then for y, it has to be binary. Yes. I'm not sure I understood your question. It's on this table?
No. It's on the result on the equality between at the beginning.
The very beginning. Okay.
I saw the results like empirical, so I'm not sure. Like this one.
Yes.
Yes.
So the question was now going to
in this space of y hat and a, actually the distances are, I guess, there are not many so many distances possible. I think 0, 1, or 2.
Yes, actually, to get this, it's not so hard. It's mostly calls for like the link between also the Wasserstein distance and the total variation. And actually, we went through total variation because in this specific case, it's quite straightforward, to be honest, to get there. Yep.
Like, I can have a look.
Okay.